of people now, so we can begin. Hello, everybody. Thank you for joining us all today. It's really a pleasure to have Yuan and Ting here, talking to us about this new era of galactic archaeology that he helped usher in. I've known Yuan since my first year of graduate school, and his work is consistently impressive and on the cutting edge. And so he's been, rewarded for that through the NASA Hubble Fellowship, which has brought him to the Institute for Advanced Study, as well as Princeton Carnegie Fellowship. He's supposed to be starting as faculty at Australian National University, but COVID has kept him at the Institute for Advanced Study for the time being. He welcomes any questions during his talk, but of course we'll take questions at the end afterwards. And so I'll hand it over to you, Yuan. Thank you for joining us.
Okay, good morning, everybody. It's really a pleasure to be in Canada, kind of. I'm really it's really bummed because I couldn't come to Waterloo, which is a town that I really want to come. Okay, but anyway, science. Let's talk about galactic archaeology. So today I will focus on the Milky Way. So I work on both the Milky Way and cosmology. I will be presenting today is really thanks to a series of good students that I have the pleasure to work with, and two of them are actually on the job market this year. So do look up for them because they do really good work. So because it's COVID time, so let's try something different. So this is a take your adventure talk, meaning that at some point of the talk, you will have the choice to take the talk in a certain direction that you want. So you can use the Zoom reaction button, and I will just glance through the word and see where I should take those talk. Okay, so let's get started. Okay, so first of all, just the background, right? Just one slide's background. Why do we study the Milky Way? Right? There are hundreds of billions of galaxies in the cosmos. Why do you focus on one? And this is for good reason. So just to remind you that, first of all, the Milky Way is very representative. So most of the spiral galaxy is like the Milky Way. So it's a very typical L-star galaxy. But also, it's really due to necessity, right? Because the Milky Way is the only galaxy that we can really study in great details because we are embedded inside the Milky Way. So the movie there on the left is zooming in from the Milky Way to the Earth. So this is why we still study the sun, because the sun is the closest star to us. And the same thing for the Milky Way, is the closest galaxy to us. And you might wonder, why do you want to why is it so challenging to understand the Milky Way? Why shouldn't we have understood all about the Milky Way? Because we are inside the Milky Way. And the reason is because we actually understand quite little about the Milky Way because we are literally embedded inside the Milky Way. And the analogy that I use 200 times now is that you should think about spiral galaxy as a big piece of pizza, and for the Milky Way, you are like a little broccoli stuck inside the pizza. So if you're like a little broccoli stuck inside a pizza, then it's really hard to see the whole pizza because you are blocked by the cheese and the mushroom and the pineapple that are along your way. But this field is really changing. In the last few years, it's one of the quickly changing field in astronomy. So what I'm showing here is the survey that we have in the last 2 decades. So the y-axis here is showing you the number of spectra that we are collecting from this survey, and the x-axis is the spectral resolution. The dashed line here that you see is more or less like the telescope power, so sort of the integrated time, if you want. So in the past, we are sort of stuck in the top, at the bottom left corner, like what I call a prehistoric time, which is not too far ago. Instead, a part of my PhD is using old data. And nowadays we are here, and just to remind you that the y-axis is in the log scale. So we are in the regime where in the last 5 years we have increased the number of spectra that we have from the Milky Way by about 3 orders of magnitude. And there are only very few subfields in astronomy that you can really say you increase the data by 3 orders of magnitude in 5 years. And this is, of course, not going to stop. There are lots of surveys that are coming along in the next few years. So they are all in the top left corner here. Some of them should be like starting to take data now, but it's slightly delayed because of COVID, we all know. So with this, okay, so besides the number of spectra, but it's also important to remind ourselves that it's not only the number of spectra that is important, but also the coverage of the Milky Way. So on the right-hand side here, the red dot that you might even struggle to see is a region in which we have good quality spectra in the past. And on the left-hand side here is what we have now or we will have in the next few years. So we are covering the whole Milky Way now. So this is for spectra, but of course the same apply to astrometry. So looking at the movement of star. So on the right is what we have before Gaia. On the left is what we have now with Gaia. So this is also increasing the sample size by about 4 orders of magnitude. So with this background, then there are basically 2 questions that I hope to discuss with you today. One is that now we have the big data, the question becomes what we can do with that, right? So I will talk about first part more about the statistic part. How do you use a statistic to harness information about the Milky Way? And the second part will focus on more cutting edge idea on machine learning to really get beyond some of the impasses that we face in astronomy. So let's start with the basic. I call that the Galactic Archaeology 1.0, the classic. So the basic idea that you should keep in mind is the following. So I talk about astrometry, I talk about spectroscopy, but of course we are doing more than just the astrometry and spectroscopy. So at the same time, for example, we are collecting the photometry of stars, which will be a big thing in the next 5 years with like LSST and Euclid and WFIRST and CSST. At the same time, we are having like astroseismology test is going strong. Plato is coming online. So these are collecting the light curve of star. So with all this information from star, the idea is that you should be able to tease out things like the kinematic motion of star, the chemistry of star, and how old the star are. And once you have these millions to billions of a tracer, the one thing that you want to resolve is the history of the Milky Way. So this is, for example, the star formation history, the ISM history, and how the star move around. So the game that you want to play is the following. So the idea is that now you have the pizza that you observe, and you try to understand how the chef make the pizza. So there are basically 3 steps to make the pizza. The first part is when and where the chef put the ingredient, the star formation history as a function of radius and time. When the chef put the ingredient, what are those ingredients, the ISM metallicity. And you also want to know, after you have put the ingredient, when you bake the pizza, what happened to the ingredient, how they move around on the pizza when you bake the pizza, right? So this is just a simple idea of you can forward models and do a Bayesian inference to tease out some of this information. The challenging part, of course, is that you have the selection function, because again, we are like little broccoli stuck inside the pizza, so you do not see the whole pizza. So you sample a slice of the pizza and you try to include that in your inference. But this can be done. And the other challenge is that all of this ingredient, of course, has very degenerate observational signal, not completely degenerate, but they are kind of degenerate. So the only way that you can even understand the star formation history of the Milky Way is also you fit for the ISM history and also the movement of star all simultaneously. So at this point is the first point of adventure. So you can choose to understand more about the chemistry or the dynamical evolution of the Milky Way. So I will let you choose and see the votes. You can use the reaction button. Let's see. It's very even though. But I think I would go with the chemistry. I think it's slightly more people talk about the chemistry. Oops, sorry. So the chemistry. Oh, sorry. I need to move away my Zoom because I cannot see myself. So to remind you that one thing they can tease out with this inference is using the star to understand the ISM from which the star formed, because the star formed from the ISM. The challenge, as I mentioned, is that in order to understand the ISM, you do not only need the ISM, but you also need to fit for the other things. But once you fit all of them and marginalize the other two, then you can get something like this. So on the left-hand side here, what I'm showing you is the metallicity of the gas from which the star formed as a function of a look back time at different radii. And on the left-hand side is just a illustration of how the Milky Way go from no metallicity and light up to have more and more metallicity. And just to remind you that this is not a simulation, this is sort of the big data that give you a precise constraint on the ISM, including the selection function. So you might be a bit like confused, like what is the importance of this, right? So for people that are in the Milky Way, this is kind of interesting because all these constraints give you some understanding of the processes in your simulation. But for an observer, this map can answer quite a few questions. So one question that you might be interested is where the sun was born, right? So the sun is currently at 8.2 kiloparsec from the galactic center, but we know that star can move around, so the sun might not need to be formed at where it is now. So to answer this question, you can read off this from this plot, because we know that by definition, the sun has an M over H of 0, because all this metallicity is scaled with respect to the sun. And also we know that by independent observation, the sun is at 4.6 billion years old. So just based on the ISM history of the Milky Way that you can constrain from star, then you can say that the star is most likely to form around 7.8 plus or minus 0.6 kiloparsec. So meaning that the sun has moved outward like a little bit, but not much. In fact, like it's within the uncertainty. So the sun basically have not moved much since it was born. So this is a fun pub fact that you can give in a pub, but also in terms of science, this is actually an interesting idea because this idea ties to the ideas of chemical tagging. So basically put the star back to the birth radii of the star. And some of the inference is very hard just because the star can move around. But once you have this constraint, you can put all the star that you know both the metallicity and the age, say from astroseismology, back to where the star were formed. So then your chemical models become a simple one zone models. So once you can put star back to the birth radii. This is one reason that you should care, but the other reason that you should care is that, of course, the Milky Way is an amazing test bed to understand stellar physics, right? So in particular, the stellar yield. So just to remind you that all these spectra that we get can give us more than just the metallicity. So it can give us individual abundances. So you can play the same game by mapping out the evolution of different chemistry, but this time with different elements, the iron and oxygen in blue and red. And because you know that different supernovae, of course, give you different ratio of elements. So the right-hand side might be more boring, but you can, if you believe your yield table, then you can turn that to the left-hand side, which is the ratio of supernovae type 1a versus type 2 that happen at a different time and different radii. So this result is quite preliminary. The reason is because the stellar yield table is really quite uncertain. But the left-hand side is that it's a very loaded plot, because what you can tease out from the left-hand side is, for example, the progenitor mass of the type 1a versus type 2, and also, for example, the delay time of type 1a. But as I mentioned, it's very preliminary because the yield table is hard to be sure. There are lots of yield tables, but they are kind of all over the place. So one thing that we are thinking to move forward is that we do not want the left-hand side to come from the yield table. So the left-hand side can be, for example, constrained with ZTF or LSST, right? So if you look at the Milky Way-like galaxy, you can really constrain the type 1a versus type 2 as a function of redshift that gives you the left-hand side, which means that if you have that from the transient survey and the right-hand side from the Milky Way, then you can in turn start to refine your understanding on the U table. So this is something that like my group has been like working on, but hopefully will give you some more result in the near future. Okay, this is great. So this is another life is full of choices. So I can tell you a little bit about the kinematics of the Milky Way, like a little bit, not a lot, but we can also save time for machine learning. So we'll see what you think. Wow, why all the woods are so even? Okay, I think it's slightly more on the kinematics. I need to learn how to minimize my zoom. Okay, so the kinematics. So as I mentioned, when we do this fit, one thing that we can do is also understanding how the star move around, because you need to fit that in order to understand the ISM, right? Because there's a degeneracy between whether the chef has put a different ingredient at different radius and time, or the ingredient have moved around. So if you marginalize over the other two, then one thing that you can try to understand is the movement of star. So just to remind you that star do not stay in the orbits that it forms. So we have already see that for the sun, star form in some places, but then it move around a little bit. So for the sun, it get quite lucky, it does not move as much, but this need not to be the case for the rest of the star. And there are two reasons why star move around. So one is that the star will scatter with the GMC that tend to move things around. And the other reason that star move around is that the star will coast with the spiral arm. So this is sort of like in the initial frame, but if you look at in the co-moving frame, is the following. So the star will actually like move in this horseshoes orbits in the co-rotating frame. And because this is only for like one transient spiral arm, and because one spiral arm, because it's transient. So when you have many transient spiral arm, what happens is that you have like a diffusive process in radius due to the fact that the star moves with the spiral wave. But the question is, what really causes that, right? So there are two things that can causes that. The question becomes A, how much the star have moved? You can we quantify that? And B, which one is the more a dominant source? And this has been a huge debate, but it's only until with data you can see that some of these results is really new, and it's really with Gaia and Apogee that we can now put a constraint. So on the right hand side here is showing you if a star formed at 5 or 8 kiloparsec, after some time, what is the distribution of the orbit? So of course, this is a probabilistic processes. And the left-hand side is just a face-on view of the diffusion of the orbits. The number that you should remember is basically the star move around a galactic scale length per half a Hubble time. So it's about 2.5 kiloparsec per 6 gigaton years. But as I mentioned, perhaps more interestingly is which one is the dominant source. And it turns out that the two processors have very different observational signal, because the coasting with the spiral arm will change the z dimension angular momentum. We change delta LZ that we call churning. The scattering, of course, is more random. It will change the ellipticity of the orbits. And that can be characterized by sort of the R radial action, which is sort of the R angular momentum. It's not exact that, but it's really measuring the ellipticity of the orbits. But the important point is that you can see the number is quite different, meaning that based on the Gaia and Apogee data, you can say that the star are mostly moved because of the spiral arm, but not the GMC. So it's actually 10 times more effective. between the churning and blurring. And people are familiar with this field know that this has been like a largest debate for the last 2 decades in the Milky Way disk dynamics. But it's with data now that we can really pin that down. And this is really quite well received. In fact, my student won a prize for this paper. So, and she's also on job market. So so her name is Nash Franco. So you should try to get her. So this is great, but I think it's a good point to take a pause to take a step back to understand why do we care about all this big data in the first place. And just to remind you that like in the past, when we have few hundreds and few thousands of stars, you can study the mean trend of the chemical or evolution or the dynamical trend. This gives you a very qualitative understanding of the Milky Way. And then you wave your hand quite vigorously and claim that you understand the Milky Way. But things have changed because now we have like few hundred to few thousands of stars. So not only we can study the mean trend, but we can study the distribution of the properties. And of course, when you have a distribution, this define a likelihood. And this gives you more quantitative constraint on the Milky Way, which is what I have presented just now. But this still leaves the question like, well, to do this, you do not need to have that many stars. You can do that with like few hundred thousand of stars. But we are really getting more and more spectra. And what is the gain there? So I think the gain does not come from this large-scale Bayesian mapping of the Milky Way. The real gain has to come from the statistical clustering of stars. And this can really be understood with the simple thing that we'll talk about in the next few slides. So I call that the Galactic Archaeology 1.5, the Beyond the Classic. So it can really be summarized with, this plot is a CMB. Of course, I don't study the CMB. I study weak lensing, but not CMB. But weak lensing, CMB is amazing because remind you that all this information about the cosmos that we get come from this small fluctuation that we see on the CMB, right? This is not the CMB, but this is the Gaia data. So I choose a sky projection of a Gaia data. And one thing you can see is that the Milky Way is not in equilibrium. So there are lots of small scale fluctuation in the and I call that like the char spot. And for like people who like food, this is called the lepidizing of the pizza, right? So you have many char spot on the pizza that really give you not only the information of the chef, but tell you a lot about the oven that you bake the pizza, the heat sources and the diffusion of the heat sources. And we know that these heat sources exist because a cursory glance of the pizza gives you the galactic evolution, but understanding the char spot give you the heat sources. So what are the heat sources? This includes things like star cluster formation and how it disperses over time, and how supernovae inject a chemistry to the Milky Way, and how the ISM diffuse them. It starts through these local heat sources and the diffusion of which you see all these char spots that you see. Which means if you can somehow characterize the char spot, then you can start to constrain the subgrid of physics of the Milky Way. So we try to do that both in the chemistry space and the kinematic space, but we'll focus on the kinematic space today. So one thing that we try to do is to understand what char spot you should expect to see. And then we immediately run into a problem because in order to understand the clustering of individual stars, you need to have a simulation that resolves individual star, right? And this is is infeasible in n-body simulation because we are talking about hundreds, billions of stars, and this is not including the dark matter particles. So we need to reinvent new type of simulation that allow us to resolve the individual star. And roughly speaking, what we try to do here is to build a heuristic models to overcome the interaction between stars. So we let the star orbit with some potential, and the interaction between stars is mimicked by some heuristic. So we make more assumption than n-body, but it's the only way that we can get to the individual star while not sacrificing too much of the simulation, the fidelity of the simulation. And to my best knowledge, this is perhaps the only Milky Way simulation that do this kind of thing. So it's really a happy medium between n-body and semi-analytic models. So there are lots of Gaia mocks. They are doing some sort of analytic models in painting star onto the n-body, but it does not really help you to understand the dynamics of individual star.
Sorry, what simulation did you say this is?
I'm sorry?
So which simulation is this?
So this is the Kamda, Conroy, and Ting simulation. We don't have a name.
I don't have a name.
We thought about that. Like maybe we should have a name, but it's like a group of like people. Like so, we did not end up to have a name. Okay. But good point. If you have any a suggestion on the name, we would love to have that.
Okay. Well, thanks.
No worries. So. This simulation is done, so now we can understand the char spot of the Milky Way. And just to remind you that like pizza, even with have the same recipe and the same oven, each time the pizza will come up slightly different, meaning that the process is stochastic, but you want to capture the essence of the system. So you need something called the summary or steady state of the system. And this is not new in cosmology. People do that with Galactic, but of course now we can do that with star. So one summary or statistic that we look into is the two-point function, right? Because just borrowing this idea from cosmology. And just to remind you what is a two-point function, it's a function of the separation of the star. And you want to ask how many pairs of star do you have in the data that have this separation compared to the case when the char spot is completely random. It's like if you have a very heat sources, then you have a big char spot, but this is not the case if your heat sources are quite random and even. And the normalized version of which is what we call the two-point function. So we try to characterize that. So this is sort of the results. So I'm plotting the two-point function as a function of separation. The white dashed lines show you the data from Gaia. The blue points show you the simulation projected to the observation space. So we include all the selection function from Gaia and also all the uncertainty. So you can see that this is a good agreement, meaning that we have include enough subgrid of physics to see the char spot. But perhaps it's more interesting when you turn off some of the heat sources, right? So one thing that we turn off.
Can I ask you a question about the definition? So how do you define random pairs for the Gaia?
Yeah, so this is, of course, you need to take into account the selection footprint. So what we try to do here is to map out the 6D phase space of the Gaia. So if you just draw from that 6D phase space, then it's random, right? Because if you have only the 6D phase space distribution, you are drawing the one-point function, and that will erase the two-point correlation. So that is what we call the random.
Yeah, but you need to do some sort of a smoothing to be able, because I mean
yeah.
So, okay, so what is the smoothing that you do, or is
so we use something that I will talk about in later. It's something that is called the normalizing flow, which is a technique in machine learning. So the idea is that if you have only a realization of the potential, how do you get back to the if you only have a realization of the distribution, how do you estimate the distribution, right? So this is called the smoothing. But in the world of machine learning, there are better tools that go from a realization back to the distribution. But the simpler way to think about this is like a GMM. You can do that with like a Gaussian mixture models and fit like a maximum likelihood, but that will not be very robust because the phase space is quite nasty in Gaia.
Mm-hmm. Yeah. Okay, thanks.
So this is a great question. So and then we try to turn off some of the heat sources, right? To see what is really necessary to create this two-point function. So one thing that we erase is, say, for example, remove the GMC from the simulation. And just off the bat, you will see that if you do not have GMC, then you will over-predict the number of pairs, which is not surprising because the GMC tends to disrupt the pairs. So once you remove the GMC, you over-predict the number of pairs. So this is really like the first study. Now we are running a suite of a simulation, say with like a different number or density of GMC and the cluster mass function of the GMC. And this gives you a way to constrain, say, something like GMC that is very hard to see in practice, and it's really hard to constrain.
So are you separating like stellar populations by age or not?
Yes, so this is actually, we actually in the study, this is all ages because we just use the same color magnitude cut of Gaia. So this gives you some age distribution. But in the paper that we wrote, we also sliced that with ages. So if you have additional information like stellar ages, you should be able to get stronger constraint, right? Because different population should have different 2 points. But that is hard just because not all Gaia stars have stellar ages. So this is sort of like integrate over the age distribution.
Right, like, you know, but in the simulations, at least, you know, which way does this go? I mean, like, you know, do you expect like the younger stars to be less clustered or more clustered than the older stars?
So this is a very great question. So I will sort of like, as I will show later, most of these 2 points come from sort of like disrupted clusters. So the signal goes down quite quickly with age because of the dispersion. But the important point here is that even the cluster is completely like disrupted because the Milky Way is still collisionless. Even does not show up as a bump in the phase space density, it will still create these patterns that you cannot see. So the 2-point function can also survive for quite long. I forgot the exact number, but it's definitely more than like a giga-year. So most of these are even at like 4 or 5 billion years old. They still have like an excess of 2 points. Does that answer your question?
So at this radius, what? So like the dynamical time is like a few 100 million years?
Yeah, it's few 100 million years. So the question, the thing is that after 10 of a dynamical time, this 2-point function still survive. Not completely, but it still survive. This is very different from looking for clumps in the phase space because those things get dispersed quite quickly. So if you look for like clumps, then you cannot see things after like few a dynamical time, maybe like 1 or 2. So I think this point comes back to the fact that the phase mixing itself it's not really completely phase mixing like in the Milky Way. So it does not really fully erase the 2 point.
And that's just because the velocity dispersion is so small, I guess, compared to the circular velocity.
I guess that is right. So which means that some of these 2-point function at the OH also give you a very nice constraint on the initial dispersion of the cluster. So this is something that we are looking into with some people working on the turbulence of the gas. But this is a good point. I haven't really thought too hard about that.
Okay, great. Thank you.
No worries.
So have you tried looking at the clustering in the action space?
Good point. So the thing that we try not to do action space is because we try not to do things in the potential or dependent way. Because we believe that will increase some of the systematic. I think in the paper, we definitely look into that when we do the paper, but I forgot if we write that in the paper. Some people look into the action space. My position is that those will create like extra systematic because we are working with like a live potential, and if you do action by integrating with a fixed potential, it might be smearing things out.
Yeah. Okay.
Yeah. So the other heat source that I sort of like try to remove is, of course, the cluster star formation, right? So if I form star randomly in the plane without forming star in cluster, then the 2-point will drop quite drastically. And this is not surprising. This basically shows that what I have talked about, which is all of this signal, most of them come from conatal star. They are in the process of being like disrupted. But this leads to an interesting question about, wow, this dropped by a lot, meaning that a lot of signal do come from stars that are born together. So then you can ask from the simulation, what is the fraction of pairs that come from conatal disrupted star cluster, and what and at what scale the resonances start to kick in, right? And the surprising thing is that this is like in cosmology, the 1 halos and 2 halos term, if you want. But it turns out that this drop off of co-natal star is very, very far. It's like 30 parsec, which is very surprising. And then we subsequently do a lot of follow-up study. I think one of the key results here, like beside the 2 point, is that star do stay, the co-natal star can really be identified by just co-moving. So even a co-moving pairs with a separation of tens of parsec, which is hundreds or 1,000 times of that of the binary, they are still co-natal. So we actually try to observe some of this with high resolution spectra and show that this turned out to be true as well. And this is also like a very distinct what we are doing now compared to the rest of like galactic archaeology, because a lot of people are looking at this scale, right? Like the resonances or like the and the Hercules scream, and we are looking at this regime using the 2 point to understand the initial dispersion of star cluster and also like the GMC. Okay, so upshot, the kinematic clustering of star do reveal galactic perturbation and cluster star formation. It's just like how people do that for cosmology 2 decades ago, and now with new simulation and new understanding of the Milky Way, you can do that with stars. And I think this is really exciting. And my student is also applying job. This student is applying job next year. So Hershel Kamda, and just remember his name. Great work. Okay, so let's move on. In the rest of the talk, I want to talk about the machine, which is something that I'm more excited about in the last 2 years. So galactic archaeology with the machine. But the segue that we did for the first part actually is a good introduction about what is the bottleneck that we face in galactic archaeology or astronomy in general, and how do we solve that with the machine. Show you a few limitations. The first part, we talk about feeding models to the Milky Way, right? The kinematics and the dynamical models. But we all know that the feed is as good as the models. So take the example of the galactic halo, right? So if you have assume a triaxiality or not, you will change the halo mass by a lot. And this means that, is it possible to go beyond parametric models and really let the data speak for itself? There are lots of people that claim they're doing non-parametric models, but they're kind of like weak. They are just sort of like doing beam dynamics, but not really doing full beyond parametric models. So this is one limitation. You think about the core and cups problem of dwarf galaxy, or the detection of intermediate mass of black hole in the other galaxy. They're all sort of like plagued by the idea that we need to have models, and the systematic of the assumption is the largest uncertainty of the constraint. And the other limitation is that the second part, we talk about the 2 point function, comparing the simulation with observation. This leads to 2 major problems. One is that, why do you use 2 point, right? So like the Milky Way is clearly not Gaussian, and 2 point does not capture all the char spots that we see in the Milky Way. So to really get a very good result, we need to go beyond 2 points. And I think that, like the philosopher Abraham Maslow say, if you only have a hammer, you think all things are nails. And the same idea here, if you use 2 point, then you can only do so much. So you need to go beyond that. And the other reason is that, of course, the simulation that we generate is never perfect. And this is why we do astronomy, right? Because we are missing some of the physics. But the paradox is that because we are missing some of the physics, means that your models never really fully replicate your observation. So how do you go beyond that? So these are sort of like the 3 I call dark cloud in galactic archaeology, or like in astronomy in general. But turns out that all of this can be solved by machine learning. Big claim, but I hope to convince you that that's true. So depending on how much time we have left, all of this topic I have worked on this year, I will encourage you to read some of this, because these are really like my main research focus on nowadays. So let's talk about the first part. How do you go beyond parametric models with machine learning? And this might be a good point to really explain like depends on where you stand. So some people are very skeptical that you can use machine learning to do physics for good reason, because like the machine is so flexible that the machine might not satisfy the universal laws of physics, right? But then the question becomes, what is really the fundamental of physics, right? So if there are something that is fundamental that you believe to be true, there are no stopping of you to encode that in the machine. And perhaps a galactic dynamics is a very good example. So the large part of galactic dynamics can really be reduced to a simple equation here, which is the total derivative of the distribution function. And the point here is that you want to go from stellar tracer, like the distribution of the velocity and position, to the potential, right? So this is how you connect F to phi. But of course, there are a lot of, this is just the definition of a derivation. But of course, you cannot make a progress with so many terms. So what we call the fundamental assumption of galactic dynamics come down to two things. One is that the system is called collisionless. So with that, you can kill off the first term. And that is not good enough because you still have many terms. So the other assumption that you make is that the system is stationary. So once you kill off this term, then you are in business, because now you are left with the following terms, which means if I somehow use this part as my optimization function, if I use this as the loss function and try to minimize that in my machine learning, we are encoding the fundamental assumption that we hold to be true into the neural net. And this is a very active field that called physics inspired neural net. So people have doing something like encoding the Hamiltonian or Lagrangian into the neural net. But we take one step further and ask the question, what is the fundamentals of galactic dynamics, and use that as the loss function. To show you one example how this goes, so remember what we want to try to do here is optimize this thing, but we want to go beyond the ansatz, right? So we do not, like, basically half of the Binet and Tremaine is about building the ansatz for F that give you phi. But if you know that what you really need is this equation, then you can say, can we go beyond the ansatz? And that the answer is yes, but you need a few tools. First, you need to estimate this thing, right? df dx and df dv. And first you need F in the first place, right? So you need to go from a realization of F to F, right? So in astronomy, most of the time we are looking at a realization of a distribution. And this comes back to the question about how do you build a random case? You have an ensemble of Gaia data. How do you build a function F without using the ansatz? So one tool that you can use is called the normalizing flow. You will have the choice to decide if you want to listen more later, but it's a machine learning tool that try to map a ensemble into a distribution, and at the same time give you the ability to differentiate that. So you can think about this is like a Gaussian mixture of models on steroids. So basically there's very few nasty distribution that you cannot fit with normalizing flow. And with that, then you have these two terms. Then you are in business because you want to optimize for this term to minimize for the loss function. And remember, why do you want to minimize that? Because this will naturally satisfy the Liouville's theorem and also the system being in stationary. And again, here, you do not need to assume a functional form for phi. You can use a neural net as well and try to do a back propagation to minimize for the loss function. So as you can see, after some epoch, just the fact that you want to minimize for this loss function, you will get to the true solution. So what I have shown here is that you can really go from any set of phase space tracer into the potential without the ansatz. But more importantly, the ansatz will satisfy the Liouville's theorem and being stationary.
So is there something to quantify, like the bias that you get by assuming stationarity here?
Yeah, so this is a very good question. So this is something that we are trying to see how much things breaks when you do not have stationary, right? first of all, this is what people assume. So even you do a parametric models, you always assume a stationary. But we actually start to look
things like the Gaia spiral, for example, right? You know, we showed that we're not exactly in equilibrium, right?
Yeah. So we are starting to slice in simulation because the first thing that we do is with a plummet sphere that we know the true results. So now we are moving on into real simulation and see, A, if you have break the stationary assumption, how much this thing will bias you, something that we want to do, and B, can you really map out sort of substructure? And so this is very, very preliminary, but with the fire simulation and try to recover that potential, we are able to get a lot of like substructure that you see, even the system is not in fully stationary. But you're right that with fire simulation or sort of like my student simulation, we are start to see how much we can break the assumption and still how much biases it incurs. But it's really a very exciting way to move forward because this is sort of like in the Milky Way, many things is not in stationary, but the same, I think there are lots of things that are in stationary, right? The dwarf galaxy core and cups problem, the intermediate mass black hole, those are sort of in the Milky Way where the dynamical time is extremely short. So those will be in stationary. But even for the halo, it seems okay. So does that answer your question? Anyway, yeah, we can talk more about that. It's anyway, so the point that it's sort of like a new frontier thinking about how you do physics inspire a neural network. But I think the take-home message for this part is that if you understand what you want to encode that in the machine, say, if you believe a stationary is broken, you can also change the loss function to include the physics that you only hold to be true. And then you can let the machine to do the rest. Another choice, so I talked about this amazing tool called the normalizing flow for a while now. You can choose to listen to more of that, or you can save more time for a question. I will, I don't think I have time to go through more. I think I'm at the 50 minutes. Okay, I will talk about this and then conclude. So the normalizing flow. So what is the normalizing flow, right? So the goal here is to map an ensemble into a distribution. And how do you do that? So let's say you have a very nasty distribution, like a double crescent distribution. The idea of normalizing flow is to say, I do not need to describe f. What I really need is to find a change of a variable that map f into something simpler. And more realistically, I can use something called the neural ODE that morph a double crescent distribution into a normal distribution. And the key here is that you do not want to use a neural net. So first you want the neural net to be invertible, because now then you can go back from the normal distribution back to f. And then you also need to make sure that since you want to use that as the change of variable, the function t, the Jacobian of t, better to be easy to calculate. So with these two assumptions, you limit yourself to a subset of a neural net that satisfy that. And then you can describe f without describing f, because what you really need is t minus 1. So then you can go from n, which is always infinitely differentiable, back to f all the time. So that's sort of like the thing that I heard people explaining on normalizing flow is like you have a boy band and you try to like disperse that, but not bumping into each other. So you want to have like a smooth diffeomorphism of the distribution. I was hoping that I can go for at least one more, but I don't think I have time. So I will just skip to the business. Okay, some cool stuff. I use a deepfake to do science. You can read more about that, how you can use a deepfake to do science. Very complex field. But with that, I think I will try to jump ahead and close it. How do I close? Shortcut, I think, is this one. So we talk about large-scale mapping of the Milky Way, the first two, the radial migration, the ISM. We talk about the two-point function of star to understand the child spot. We talk about the normalizing flow to solve for non-parametric solution. I didn't have time to talk about a domain adaptation and also some of the things, but yeah, I will be happy to take a question.
Wow, well, it sounds like we've got to have you back and have part 2 of this talk at some point. Thank you so much for the wonderful talk. And yeah, any questions from anybody?
So I can go ahead and maybe ask you a little bit more about this correlation function. So indeed, we had done some work on computing the correlation function in the action space, and in fact, our goal was to constrain the potential. So I mean, that wasn't kind of a bug, but rather a feature. But along that direction, another natural thing you could consider, which we haven't done, is the correlation function in the phase space.
Yeah.
Which, I mean, the structures that, I mean, were bound or formed together, they have both positions and momenta or velocities close together. So have you considered that?
Yeah, so in a way, you're right that the two-point function of the position, of course, because it does not, so in the case of like a Gaussian processes, then you are done, right? So whatever change of a variable is unnecessary because it fully characterizes the field. But in the place of non-Gaussian processes, then how do you do a change of a variable and look things in?
That wasn't my question. I think that's the non-Gaussianity is certainly one aspect, but I mean the fact that there is also the phase space in basic correlation both in velocities and position, that was the aspect I was.
Oh, so the velocity, yes. So we do slice in the 2-point in velocity. So I only show the 2-point in position. So we do look at the 2-point in velocity and given position. And because you have 60 phase space, and how do you choose the right a summary or steady state is yet to be seen. And of course, a lot of exploration in the action space will be great. Yeah.
Yeah. Okay. So I mean, I think that could give you more information about this structure, this transition region. And so basically, if you could define some basically distance in the phase space, which not just distance and velocity or distance and position, but distance in the 6th dimension.
Yeah, and also the chemistry. So like the thing that we're working on is also not only the 2-point of the position, but
Be great. But if no one jumps in and anybody else has a question, ask away.
Can I just ask one? Not that I'm a student, but so the number of wide separation binaries is kind of an interesting test for looking for dark objects in the Milky Way. Yeah. And it sounded like you had some predictions about that, but also that there's maybe the possibility to extend that with you know, proper motion pairs, right? So is that something you considered or looked at?
Yes, so please don't write my papers. Yes, you're right that we are really thinking about how to find, it's not like people have been looking for trough in wide binary with certain separation. So the same can be applied to the co-moving star. So looking for trough, like after some separation, you know, things start to drop off the binary. Sort of like, there are plans to do that. We haven't looked into that, but it's a very exciting thing, and that gives you the characteristic size of the perturber.
Right, and then I guess the other related thing was, you know, it's interesting to think that that separation of pairs itself might be something that varies. So the same way the IMF varies as a function of turbulence or metallicity, that the pair, the primordial pair separation or angular momentum separation varies. I don't know if do you think there are prospects to be able to sort of look for that effect?
Right, I think that requires stellar ages. I suspect it would be hard, and the reason is because the stellar ages, even So I have done some work to see how you can get stellar ages from spectra. So not only for the actual seismic sample, but even you take like the apogee sample, because of the strategy that we do for this survey, which is the sub-sampling, the chances that you get like co-moving pair that both have spectra and ages is very small. So there are plans. I think people do submit like open fiber requests for SHS5 to sort of like not subsample, and you look for get the spectra for the co-moving pairs, and then you can slice things in stellar ages. I think it's very difficult unless we can find some way to estimate ages more effectively without using the dynamics.
Okay, thanks.
Yeah.
Well, and I think that's all we have time for today. So let's give Yuan a virtual round of applause if possible. Thank you again for taking the time to talk. It was great. So have a nice rest of your day, everybody.
Thanks.
Happy Thanksgiving. Happy non-Thanksgiving. Bye-bye.
Bye.
Bye.